Good afternoon from Rice School of Architecture in Houston. My name is Juan Jose Castellón, and on behalf of our Dean, Igor Marjanovic, and my dear colleagues at the Lectures Committee, Maria Nicanor, Executive Director of Rice Design Alliance, and our visiting critic, Elizabeth Galvez, we would like to welcome you all to our lecture series fall edition. With the title, Building Identities, this series of lectures have the vocation to highlight the inseparable link between the construction of physical structures and the construction of human identities in our multicultural and diverse communities. Nonetheless, these construction processes involve the intentional articulation of specific methods and tools and the deep understanding of both traditional and contemporary technologies. Moreover, the current climatic crisis demands a strong commitment from all the construction sectors with a material culture that respects our natural, urban, and social environments. In this regard, it is a great pleasure for me to introduce our guest today, Philippe Bloch, and to welcome him to our lecture series in this digital format. Philippe Bloch is professor at the Institute of Technology and Architecture at the ETH Zurich, where he leads the Bloch Research Group. Together with his talented team, Philippe is developing an outstanding and substantial work focused on the design and materialization of efficient structural forms based on innovative and sustainable construction methods. Philippe studied architecture and structural engineering at the VUV in Brussels and at the MIT, where he earned his PhD in 2009. As founding partner of Oschendorf, De Jong, and Bloch Engineering, Philippe translates his research into practice, offering consultancy on structural geometry and computation for the design, engineering, and construction of novel shell structures. Among other multiple awards and titles, he is currently director of the Swiss National Center of Competence in Research, NCCR, and member of the academic committee of the Holcim Foundation for Sustainable Construction. Philippe, thank you so much for accepting our invitation and welcome to Zurich. Sorry, to Zurich, no, I'm still thinking about my time when I was there with you. Welcome to Rice.
Thanks a lot, Franco. Thanks a lot for the invitation. I very much look forward to sharing our research today. Good afternoon, everyone. It is indeed a pleasure to present to you in the next 40 minutes some work that we have done in rethinking construction, and many of the examples will be in concrete. But before going there, I want to maybe outline what drives me, or what is basically behind everything that we do in our research. So I hope that I'm preaching to the choir, but I want to nonetheless set the base here and kind of outline these challenges indeed, and be a bit more specific. In the next 30 years, we're expected to be with quite a few more people on this planet, more than 2 billion more, in fact. Bill and Melinda Gates, in their annual letter in 2019, translated this increase to the challenge that we face with our industry. In order to provide adequate housing infrastructure for all these additional people on our planet, we need to build the equivalent of 1 New York City every month for the next 40 years. I really hope that it will not happen like this, like we have been constructing in the last century, practically. And the reason that I say that is because globally we are a major polluter as an industry. So building and construction, we are responsible to almost 40% of the greenhouse gas, human-made greenhouse gas emissions. 40% of the use of virgin materials, so resource depletion is there the big challenge. 40% of global waste production, and in many areas in the world this is even much higher. And then also, of course, the energy that all our buildings use, both in construction and in operation. So with these few slides, I hope that you agree with me that we desperately need to change the way and rethink indeed how we both design and build our structures. As you heard in the introduction, I am a hybrid architect, structural engineer. So I wanted to also specify that I will be focusing in my talk, and our work in general focuses on the embodied emissions associated to the built environment. So that means everything that happens until you turn the key, until you basically start operating or occupying a building. So everything related to producing materials, construction, transport, and so on. I see this as the key challenge and a big bottleneck indeed to focus on these embodied emissions, because maybe cheekily said or naively said, perhaps even, one has a theoretical solution for the operational energy, just going to green sources, renewable sources. So theoretically, we would have a solutions to deal with the operational energy, but we still are left with the embodied emissions. In order to address really what is there a potential strategy, I like to use this equation. And don't worry, there will be not many, or this is in fact the only real equation. And I borrow it from my colleague, Catherine de Wolf, who did her PhD at MIT with the same advisor, John Oxendorf. And she describes here, or she dumbs down, simplifies the global warming potential to this simple equation that really kind of outlines what really matters. So she says that you basically want to take the sum of all the parts in your building, and then what matters is the mass, so how much material that you use, and then, but also this ECC. ECC stands for embodied carbon coefficient. So this is basically a representation on how polluting, how bad a material is towards the climate. So you see that it's not just about building lighter, so with less material, but it's also about using the right materials, low pollution materials, and so on. And then lastly, you see that all of this wants to be divided by the time that a material is used. And that's, of course, the framing of circularity, where we want to ideally extend the lifetime of a building by designing for future use and adaptability and so on. If that's not possible, we want to somehow try to design for reuse, so reuse of components, of parts. And again, if that is not possible, we want to have an outlook of an efficient recycling to keep the materials at least in the cycle as well. So this equation to me kind of really clarifies what we're after, how we can combat embodied emissions. And it becomes also very clear that as a structural designer, you can have quite a bit of influence here. So our group approaches this problem with two concepts. So the first one we call strength through geometry, and the second one material effectiveness. And I will explain both indeed, but they're of course related to the equation that I just pointed out. So let's first look at strength through geometry, and I'll do this by walking through a few projects that we have done. So I want to start with the Armadillo vault that we built for the 2016 Venice Biennale. What you're looking at are 399 cut pieces of stone that are held together by gravity and geometry only. So there is no mortar, there's no glue, there is no reinforcement holding this together. So this is really already demonstrating that what you can achieve when you get indeed the geometry right. The reference here, or the inspiration, is of course, in fact, I did my PhD at MIT with John Oxendorf on the assessment of historic structures, these beautiful structures, and trying to explain and find tools to explain why and how they're standing and how long they'll still be safe. What you might not see in these beautiful fan vaults here at King's College from below is that if you were to calculate the thickness of these large stones that are kept in compression because they have a good geometry and not because we're adding materials or reinforcements or high-tech kind of things, that the thickness of this shell over its span would be proportionally the same thickness, or should we say thinness, as an eggshell. So this to me was absolutely mind-blowing, and it made me also realize that perhaps modern engineering had forgotten also some key concepts that made these kind of structures possible. So we have been developing tools, also graphic statics-based tools. That means quite intuitive kind of methods that allow you to rediscover these kind of geometries. And we also feel very strongly about sharing everything that we developed. So this is, for example, a print screen of this shell being, the initial modeling was done with Rhino Vault, a tool that we share openly so that others can also discover, like we do, this same kind of elegant geometries. But again, I want to here maybe emphasize, so this super thin sheet of just 2 inches in thickness of dry assembled stone is stable, is safe indeed because of its geometry and not just by adding materials. Here you see the team out of Austin, Texas, the Escobedo group, assembling indeed this spectacular statement. We did this crazy thing, this crazy vault, not necessarily because we need more stone vaults in the world, but to shake the community, to show what you can achieve indeed through geometry. You can activate these humble materials, and you can indeed rediscover the elegance of why cathedrals are still standing after centuries indeed. A next project that I want to show that fits in the framework of strength through geometry is one that I was very lucky to be involved with Peter Rich Architects and John Oxendorf. It's the Mapungube Interpretive Center in South Africa. And this is a project with large vaults. It's a museum that is built with predominantly local resources. So both local labor and local materials. The reference here is, of course, these beautiful tile vaults that we see all over the US, by the way. This is a Mediterranean technique, a Catalan vaulting, Guastavino vaulting. So the Guastavino is built, for example, here, Grand Central Terminal, the Oyster Bar. So what you're looking at is actually one of 3 layers of unreinforced tile. But why specifically this was a relevant kind of reference is because, as you see here in this image, that the technique allows to realize these geometries without needing formwork from below. So you build in stable sections. And so that was ideal, of course, with minimal guide work. So this timber that you see here, this bent timber, is guide work because these are literally farmers and local farmers and carpenters that are building in this new technique without a lot of effort and so on. The reason that I want to, in the argumentation of strength through geometry, talk about this whole project is because the materials. So the materials were locally made. They were just soil pressed with a little bit of cement, 7% of cement to stabilize the bricks. They didn't have to be fired. There is no energy except for human labor going into this. But to me, what is worth pointing out is this image here. On the right, you see the women from that small town carrying the tiles in very small packages. And that is because the tiles are designed for, I forgot to translate what that is, for 2 megapascals in compression. That basically means peanuts in compression, 10 to 15 times less than a standard concrete. But if you hold one of these bricks in your hand, then you can just break it in bending. So an extremely appearing to be very, very weak non-structural material. But then if you look at on the left, if you place this weak material where the forces want to flow in compression, this is indeed a very safe and structural kind of geometry indeed, like they built in the past. So a small learning opportunity. If you don't have a lot of double curvature, like the historical domes or the stone vault that we have done in Venice, then you need something else to basically take live loads. So the red line, by the way, represents where the forces might want to flow in compression. And so you see that here, this red line cannot be contained within the geometry. So that literally would mean collapse. So one strategy would be to add local stiffeners. And as you see, As you can see, that allows basically a path in compression to go to the supports. If you then add a tension tie, what we have just done in the last minute or so is we basically have developed a perfectly equivalent alternative to our all too common reinforced concrete beam or floor plate, but one that uses 70% less material. Right, so this to me is very powerful. Why I wanted to talk about this project is because it shows that not only you can assemble humble materials, but these materials can be very weak. And this will become important because lower strength materials are typically significantly lower embodied emissions materials, so lower pollution materials. So that's one aspect. But then the other aspect is that at the same time, we save so much volume of materials used. I'm lucky that we can continue doing this work to kind of hopefully provide more appropriate construction paradigms to kind of fight this image I took myself in Addis Ababa. This is the current state of low-cost housing, but that's you can already probably see that this is probably not how we want to go about it. Next project is the most recent one that we built. It's the striatus that is still on display in Venice. What you're looking at is a concrete 3D printed, unreinforced masonry bridge. With this project, I kind of wanted to provoke a bit because there's so much effort, so much research going on in concrete 3D printing. And in my opinion, perhaps many of these researchers are fighting against some of the natural kind of results that you get from this very fascinating large-scale additive manufacturing kind of approach. So the reference for this project is, of course, masonry on 2 levels. The discretization of the structure is like a Roman arch with large kind of stereotomic pieces. And then on the level of the 3D printed elements, we also align all the print paths such that they are locally also aligned to the dominant force flow. So that is what we are showing. We're showing another version of strength through geometry with an en vogue material that everyone is excited about. But what we wanted to demonstrate is that how we approach the design, rather than actually doing an uninformed design that you then need to start to slice up and try to see how you can print this and then do the engineering and so on. What we do here, and this is the PhD work of Shajeh, is to start from the print path. And so the print path has all the limitations of the fabrication, all the structural kind of global and local constraints encoded. So the print path becomes explicit and the geometry implicit. So this is, of course, a fundamentally different way of designing than what typically is done. And in the bridge, we wanted to show that you can actually come from both sides and that you can negotiate from the local definition that is informed by constraints and also balance this with a global idea of where you want to end up. So for this project, we use what is called a 2-component 3D printing. So not the typical extrusion-based 3D printing that we see often in the news. Why we use this 3D printing? It offers more control and indeed offers all the non-uniform layers to be aligned to the force flow indeed. But it also allows us, of course, then on the inside of the large pieces to reduce the volume and to place material not only globally along the arch, but also locally to optimize the pieces as well, which would not be possible with subtractive methods or kind of casting or things like that. So then, like a masonry structure, my team, together with with a small crew of contractors, then assembled this bridge very fast, very easy. So here you see a little bit also the very small spider crane. Only a small spider crane was needed to basically assemble this nice little structure. What is maybe interesting to point out is that we really, all the pieces are purely unreinforced concrete. So that means that they will be very low energy to recycle at the end of their lifetime. But what you also see on the right is that, again, like we showed with the stone structure, that we have a dry assembly. And perhaps for a bridge, this is less relevant. So maybe you don't want to move your bridge around all the time. But more generally for prefab construction, having this kind of self-registering compression joints and full demountability is, of course, an interesting topic if you were to think indeed of end-of-life reuse of full components and so on. So because this is the latest project, I allow to show maybe a few more images of what we did here. Perhaps interesting to point out here on the left, for example, is that all the little creases and features that you see are not frivolous. They're actually an expression of the stiffness on the inside. So all these different techniques were developed to make the bridge really speak the language of the fabrication and the structural constraints. Also, here on the side, you see these additional lines in the balustrade blocks. They are actually the imprints of changing the nozzle and making the stiffness on the inside. So again, you see that we try to celebrate and globally coordinate and these features so that they could also become potentially an exciting architecture. This project was done together with Zahadit Architects, specifically with a computational and design group led by Shajeh. And the amazing 3D printing was done by Incremental 3D out of Innsbruck. And the ink, the concrete ink, was developed by our partners Holcim. Here are a few more images. These creases that I was talking about, these features that appear are really are an artifact, but an artifact that we then control that comes indeed from the internal logic and other aspects in the 3D printing. So as I said, it's still in Venice. It's only for a couple of more weeks. So if you happen to go around, be in Europe, then still go check it out. The next project that I want to show is nitkamdela. There, I'm shifting gears a bit. It's actually no longer about strength through geometry, but about how to realize these non-standard geometries in efficient ways. Another collaboration with Zaha Code. This was a pavilion that we built for the largest exhibition of Zahadit Architects in the Americas. This is a thin fiber reinforced concrete shell that we call nitkamdela. It's of course doing homage to the shell builder Felix Candela in Mexico that built these spectacular geometries, 30-meter spans. So what is that? 90 feet spans with not even 2 inches of structural depth. So these are absolutely spectacular. But of course, they come also at a cost. The formworks are not easy, they're labor intensive. So these are things that we can no longer imagine nowadays. And the same is true for modern curved concrete structures like the Rolex Center by Sanaa here in Lausanne. If you look how this beautiful structure was built, then you see that on the left that we need a full foundation. Then we have quite a lot of scaffolding and so on. And we built then this super beautifully detailed timber construction that will last 28 days until the concrete hardens. And then sadly, it's turned into a pile of single-use trash. So this research strand, we try to kind of go against that and fight basically the brute force approach, which a traditional rigid formwork kind of is. You need to use a lot of material to keep the wet concrete where it doesn't naturally wants to be. And on the right, you see then the idea of a flexible formwork where you use, for example, a pre-stressed cable net to carry the wet concrete and then a fabric to cast on top. So in this project in Mexico, we used a knit, so literally the same what is used for a sweater or to make a technical brace for your knee or something like that. So we used such a knitting machine to make this ultralight formwork that could then be knitted indeed on a typical knitting machine. And on the top right, you see then arguably the largest scarf in the world being knitted by Mariana and Lex, and then vacuum packed. And then literally the entire formwork was brought on site in 2 suitcases, traveling economy from Switzerland to Mexico. This then allowed on site to install this knit. And what's maybe interesting to point out here is that all the complexities of the geometry. So this is a stiffened shell, so with stiffness running in both directions. All of this complexity was basically embedded in this one logistical device, in this knit that basically allowed us to work together with local laborers, with local expert concrete finishers. And so it allowed us basically to use the best of digital introduction into and combine it and enhance also local crafts and local kind of opportunities. In this project, we left the knit in place as a unique kind of insight or texture or aesthetic even to the shell. But here in the top view, you see how thin the shell is. It's indeed only just over an inch thick. And then in between the fabric, you actually have this double layered stiffness running. So all of this was possible with this very simple formwork indeed. What's maybe interesting here is to look at some numbers. So we realized 500 square feet of surface area, which translates to 5 tons of concrete. The entire formwork cost only $2,500 US. And as I said, this 25 kilograms, so a little bit over 50 pounds was the weight of the formwork. But what's maybe perhaps even more interesting here is not just the efficiencies that you get in the shaping and the flexibility that you get, but it's also that between the invitation email and the opening of the exhibition, there were only 3.5 months. And if you do the calculation and you were to have to mill such a formwork, you would be easily milling for 3 months nonstop. And in this case, the formwork took only 36 hours. Which of course also allowed us to extend the time of prototyping, getting our engineering tools all synced and so on. So by the way, this is also a demonstration of also rethinking how we collaborate. We do this through our computational framework Compass. I will talk about this later as well. But so this is also a necessity to introduce these kind of innovations. But what is better than sending 50 pounds to the building site is, of course, sending only data. And one could imagine, of course, with these knitting machines being readily available all over the world, that this could be a decentralized kind of fabrication approach. Okay, this was now a pavilion, but we got to build, this also got inaugurated a month ago, roughly. The highlow units, which stands for high performance, low embodied emissions. We kind of wanted to make a bit of a statement. The roof is total overkill, total crazy, but it gives at least someone a very exciting office space. This roof was built within, actually within 3 millimeters. So this is just very small tolerances. We realized this project on site with typical industry partners. So this is not, this is one of the key demonstrations here. And so we used this 100% reusable kit of parts that we had developed and also used for our full-scale prototype to build this efficiently, on time, on budget, on site. So this was a kind of a nice achievement. But I'm excited to talk about this project because it was also the premiere, the first time that we could show our floor systems. And so here you see that the floor has something recognizable. It has double curvature like you see in many of our projects. But what you don't see is that for this 5 by 5 meter space, so what is that, 20 by 20 feet roughly, we span space with only 3 centimeters. So that is just over an inch of unreinforced concrete. Okay, sorry, Compass comes here suddenly in between. So all of this was possible, coordinated through our open source framework. So as I said earlier, we not only share tools, but we also share all our algorithms. And not only us, many people at ETH, also now MIT, Stuttgart, and many other institutions are starting to share all of their algorithms in a compatible way through Compass, through this open source framework, which was initially developed and launched by our research group, developed by Tom van Mele, as you heard earlier, with whom I co-lead the research group. So this allowed us to bring this innovation into a real project, but also to coordinate all these different partners with varying degrees of computational or even digital knowledge and expertise, and to bring all of this basically smoothly on site. But I was talking about the floors, and indeed, let's focus a little bit on building floors. The reason that I say that is that another kind of translation of this One New York City every month for the next 40 years is that many of the urban areas will densify. We will have need for these typical medium high rises, 10 to 30 floors, housing, offices, and so on. If you look at these medium high rises, then this is a very typical image. What you're looking at is basically the mass distribution into such a building. And you see that 3/4 of the mass is basically in the structure, which to me as a structural designer was extremely shocking to see, because what you also can then imagine is that the structure is mainly there to keep itself up, which of course is something that we should really address. If you then zoom in a little bit more, then you see that spanning space, so indeed providing floors, is responsible for more than half of that structural mass. So that means that the key bottleneck, so the most material intensive, in global numbers, 40% of the total mass of these structures is basically into their floors. So considering that we are expected to build more than 2 trillion square feet of floor area in the next 30 years all over the world, I would say this is worth to look into if we cannot find a solution. And I would also say this is perhaps quite a good business case as well. That is where I want to shift to material effectiveness and maybe also address the gray elephant in the room. Why am I talking about concrete? While everyone seems to agree that wood is good and concrete is the most evil material on the planet Earth, is that true? Is it true to say this just about the material? Is there maybe something else at play? And indeed, there is some hints that I can use. So here, for example, you see from the famous Mike Ashby on the left, and on the right, you see the ICE inventory that shows these embodied carbon coefficients. Both of the graphs are mapped according to unit mass, but you see that in both cases that concrete is actually doing extremely well. So you see in the according to the ECCs there, only sustainably sourced timber is really significantly better. And I'm happy to talk about what we need to do about having sustainably sourced timber at the scale of urbanization as growth that we are expecting and expecting to build indeed. You probably already see where this is going. I consider concrete as an artificial stone, simply put. And the language of stone is indeed the arch, is the vault, and so on. And the reason why I want to insist that we look at unreinforced concrete like that is because the very clear facts that we saw earlier, right? That if you were to use concrete as a beam, then you need to heavily reinforce it. You're basically forcing this material to do something that it doesn't want to do, to basically work in bending. And by just reintroducing these stiffened arch with tension ties, you not only save 70% of concrete, but also 90% of reinforcement steel. So this is something to look at. And now that we have a maturity of digital fabrication at scale, perhaps we can reintroduce these non-standard geometries indeed. So that is exactly what we did for highlow. So we designed a 5 by 5 meter floor plate with 3 centimeters of unreinforced concrete. You see that the stiffeners now accumulate to the corners so that they can be elegantly balanced by a tension tie. And I mean, this is not a new idea. It's an old idea that we now reintroduce because we have new challenges. We really need to find solutions to do things better. So here you see a prototype that we showed already in the Biennale in 2016. This project even started in 2011. So this is a long time coming. This is a lot of research being done, a lot of prototypes and experiments being broken, like this one here. And then you see indeed how thin, how light the structure can be. We also 3D printed at a certain point such a floor. So it's a super weak material, equally weak as what we used in South Africa. So peanuts in compression, and you can just break it in bending in your hand. We used actually the American Concrete Institute's recommendation of the required loading protocol to demonstrate that this would be a safe structure. And if you don't believe that, then this is 1,200 kilograms of ETH nerds standing on a 2 centimeter unreinforced, super weak material kind of floor, demonstrating that we're excited about this milestone clearly. But so that all sounds great perhaps, but let's maybe zoom out a bit and go back to indeed this image. So this is an image that we see all over China, that we see happening now in India at an acceleration. Next up will be the continent of Africa. So these are the typical kind of urbanizations that we see. And let's take one of these buildings, one of these typical towers, let's say 25 stories, very boring kind of, or very typical kind of a floor plate. So let's see what that means. What would it mean to introduce our floor innovation, our lightweight floors into such a building? So what we basically are trying to argue here is that more than 40% of the weight of the mass of the building is in the floors. And then on the left, you see this minus 70% earlier and 80% here. The reason that they're corrected here is because now we're talking about really high-rise construction. And so these slightly lesser kind of results have to do, of course, with fire safety, 2-hour fire ratings, and. So, okay, so let's take these two things together and calculate for this one building. If we were to introduce these lightweight floors in there, then we would save for this one building 9,800 cubic yards of concrete less. Or if that is very abstract to you, that translates to more than 1,200 concrete trucks that don't have to go to this one building site. Additionally, per floor, we save more than 14 miles of number 4 steel rebars for each floor. Or if you were to lay all of that out, it's like going from Zurich all the way to Brussels, which was a nice coincidence because I live and work in Zurich, but I am originally from Brussels. I tried to find an equivalent related to Houston, but it's almost until Oklahoma, I guess. So just to give you a sense of how much steel you would save also in this one building. But okay, I said in the beginning, it's not just about volumes. It's not just about mass. It's a bit more complicated. And so let's go back to the equation that Catherine introduced. So the global warming potential, let's remember mass is important. So indeed, how much material that we use, the impact of the material is important. And then again, how we actually think of reuse, recyclability, and so on and so on. So first, what we can have, and sorry to give you a few numbers, but I insist on doing this because there is too much talk about, as I said, wood is good and concrete is bad. So I wanted to do the numbers for you. And that is, of course, also important for us because we're now trying to commercialize these floor systems, these floor solutions to bring them to the market. And I can maybe talk about this a bit later. But using strength through geometry, we achieve two things at the same time. So we can significantly reduce the amount of volume, so basically the mass used, but at the same time, we also reduce the stresses. Remember the Africa project. So why the reduction of stresses is important is that, and you see this in the note below, is that going from a traditional concrete to a low strength concrete, you can shave off an additional 20% of the embodied emissions associated to it. So a low strength concrete will always be lesser polluting than a high strength concrete. So actually the low stresses is directly relevant as well. And we get this through strength through geometry. So just by reintroducing the arch, we actually save almost 3/4 of the embodied emissions compared to the typical floor slab, the floor slab that would be built up to building codes, up to standards and so on. But if you now add also a bit of material innovation, so for example, we go from a typical ordinary Portland cement, so a CEM1, to start to do some cement replacements, then basically we can do even better and we can add an additional kind of saving. So that means that, and this can be done today, right? So the system is ready, it's fully engineered, we build it in high-low, we reduce the volume, we have low stresses, and these kind of greener concretes are available today. So on the concrete level, we basically reduce the impact, so the emissions, by 91%. But then, of course, you need to still include a little bit of steel, so around the boundaries. And so that means that globally, we reduce with our floor plate the embodied emissions by 85%. I just want to put this on there. If there is some sustainability experts in the audience, then I will just leave it there, because this is now the real number that we achieve, 23 kilograms of CO2 equivalent per square meter. And if you actually look up state of the art, this is indeed a fraction of what a reinforced concrete floor slab would do, but this is also half of what a timber floor would do. And I can talk about this later a bit more in detail, but one of the reasons is also that we really are lighter and using less material. Why are we lighter? Because, and this sounds almost too good to be true, but what we use, rather than adding mass to solve the problematic low frequency, the transmission noises, so this is a typical thing. And so if you have a lightweight timber construction or a steel construction or any lightweight construction, you, at least up to European code, you need to achieve an average of 350 kilograms per square meter. If you don't have that, you will hear your neighbors having a party, you will hear them walk around and so on. What we actually have demonstrated in research and now fully benchmarked in the highlow project is that actually we achieve this vibroacoustical performance through the stiffness, the geometry of the shell, and not just by adding mass to it. So this is great, because that means that we also then are 30% lighter compared to the state-of-the-art timber floor solution. I want to maybe quickly share a confidential project, because we're lucky now that that architecture teams and certain investors and clients believe in this promise, and also are excited that our collaborators and partners in this venture, Holcim, have made the statement that by 2023, this system will be on the market. But what I wanted to show here in this project is that we also are optimizing the system such that we can have very elegant integration of building systems. Even extremely big ventilation ducts can fit within the floor package. And what that gives us is that we can offer our clients more floors for the same total building height, which is, of course, an important selling proposition, because it gives you more real estate, it gives you more kind of return on your investment. All right, and then the last thing that I wanted to say, unfortunately, I cannot show too much detail, but it is related to the 3D printed floor that we have done, is that the system that we are now developing is a entirely prefab system, so that it can be dry assembled like the bridge in Venice, so that it is fully demountable, so that we really have an end of life strategy in reuse. As I said, we have all these cavities which make it very flexible, very customizable, so you can basically upgrade the building systems easily, so that the building first, before having to be reused, that it doesn't get obsolete. because our disciplined approach to keep really all the materials separate, so unreinforced concrete and identifiable tension ties, that gives us a very simple and very straightforward low energy end-of-life recyclability. And then a key advantage is that we still have enough thermal mass and enough concrete to actually use this thermal mass to optimize the building system, so that we can put significantly less pressure on the operational energy and all of that. So the reason why I so passionately and excitingly present our innovation that we are now very close to translate or to offer to the market is because, again, when we look at this image, all of these buildings, this blew my mind as soon as I found this out. 40% of their mass is basically in the floor plates. Maybe a very small kind of extension, because I'm running out of time, is that we also are aware that most of construction will not happen where I live, but in other parts of the world. And that is where I'm excited. This is also on show in Venice. So if you can still go check this out, this is a collaboration with the government of South Africa to develop lowest cost housing units. And what we're basically using there is that we're using a bio-waste, shredded kind of non-indigenous plants are being used as aggregate replacement in this bioconcrete. They had already this as a system, but they used it only for non-structural kind of purposes. And we introduced even more extremely masonry logic, so that we no longer need tension ties. So we are introducing these buttresses, and that allows us then to build these low floors and so on. I ran out of time, so I had one more thing I wanted to show, but let's maybe wrap up and say that I really believe that the pressure, the urgency is there. So that is why we developed this open source framework. Let's share, let's work together, let's try to make our world better, because we have only one planet and we are a key polluter. So let's take our responsibility and let's start to innovate together. But what I talked about today is I am trying to introduce structural geometry to use less material. We use specifically funicular forms, so compression shells, because the stresses are low, and that allows us to use better material. Through computational fabrication, I didn't emphasize too much, but I gave you some hints on how you can really rethink how these non-standard geometries are being shaped to reduce the waste associated to them. And then this was not the focus, but believe me, everything that we do is can only happen when we break the sequential. An architect sketches something, then an engineer doesn't try to kill anyone, and then a contractor tries to build it as cheap as possible. Innovation will not happen like that, but also innovation will never be economical if we don't start to team up from the beginning, and from the beginning design for and with constraints. And we do this through computational methods, and we demonstrate this also with the use of Compass. So with that, I'm very excited and thankful again that I could present our work. I hope that this motivated you, and I'll be happy to take any questions if there are any.
Thank you, Philippe. I think it is a wonderful presentation, and actually is stressing the necessity to think about these fundamental questions also from a technical perspective, to also maybe escape from the mainstream discourse. Sometimes we have to be critical about the way we think about processes and materials, and I think what you are bringing are not only real numbers, but also specific projects that they are kind of showing the potential of transforming the ongoing paradigm in construction, which is, as you said, something that requires an urgent response. So thank you so much for the presentation. And at this point, I would like to introduce and thank our students, Ray Atkinson and Isabella de la Iglesia, for joining us today and taking care of our Q&A. But before passing it to them, I would like to open the conversation with a question to Philippe that relates to also ongoing discussions about the definition of a new technology culture at Rice University and in Houston. As we have seen in your presentation, your research is somehow intrinsically related to the production of multiple models, physical and digital, and to the construction of also the full-scale prototypes. And this experimental approach is grounded on a very solid collaborative model. You were mentioning this in your presentation, that involves different kinds of expertise and different fields of knowledge, including your collaboration with industrial partners. My question for you, Philippe, is how would you describe a bit more in detail the nature of this in the interdisciplinary work in your research, and also more broadly, how it relates to the material and construction culture at the ETH in Switzerland, and in relation to our global context at large?
Yeah. Okay, that's quite a comment or quite a first question to answer, and I'll try to do my best. But maybe it's useful to kind of start by sharing a little bit how our group evolved in all of this. So initially, we focused on developing new design methods to reintroduce or discover or engineer kind of more efficient form. Very, very soon, we realized that all of this is irrelevant because we need to figure out how to realize in economical, not too wasteful ways, these non-standard geometries. So we shifted, or no, we not shifted, but we extended our expertise to digital fabrication and really thinking of construction. Then when we tried to go to the building site, then we started to realize that these geometries were so weird that anyone in the project was giving 300, 500, 1,000% of risk factors on the cost, on the estimations, on everything. And so then we realized that we also need to really find mechanisms to introduce innovation in real practice. And that's where basically we are going even to BIM on steroids and more kind of approaches to actually try to interface with practice as well. And so I see that as a big challenge, is that how can you bringing an innovation demands actually not just a good idea, but demands also finding a model to collaborate with industry and to translate these things. And for me, what has worked quite well is to work actually and to build up trust with expert contractors, with experts in general, and to do this beyond the project, and to really kind of because one needs to get used to each other, and that is extremely important, because it's extremely important to realize something in the real world. This is something that I have tried to avoid for the last decade, or even 12 years. We have done so many extreme prototypes, even the project in the Biennale. This is a crazy stone vault. And then nonetheless, people were saying, yeah, but it's on the inside, so it's not really exposed. That's why we did the bridge. And that's why we do high-low. And that's why we end. But all these demonstrators are never enough, because now, for example, high-low, they say, yeah, okay, but you did this in Switzerland. Switzerland is a bubble. They're mega rich and they do whatever. Anyways, they support this kind of innovation. So this is not relevant for the rest of the world. So that is something that I just heard last week, and I didn't realize that building something real in Switzerland would be said by other people in the world like, yeah, but only in Switzerland. So anyway, what I'm trying to say is that probably rightfully so, because certainly when you do structural innovations, it literally is about life and death. So one should be careful, and one should be skeptical a little bit. But yeah. So the importance of actually building things real, I underestimated severely. But now I'm noticing that as soon as you have this entry, then things start to accelerate finally. And then you had a question about Switzerland. I'm super thankful that I'm in Switzerland, and I didn't realize this even, because compared to the Euro codes, compared to the rest of Europe, the Swiss codes are very open, very flexible. And in fact, if an engineer signs off on something, then you kind of can do whatever the engineer signed off on. And so that is a unique opportunity to be, in a way, the test lab, or kind of the laboratory, or the guinea pig for the rest of the world. And so that is something that I understood rather quickly, and that we are, of course, entirely misusing in trying to push the boundaries with our prototypes. Yeah.
That's a great answer. Thank you, Philippe. And now I will pass the Q&A to our students, right? Isabella, please join the conversation.
Yeah, so first of all, thank you so much for being here and speaking. It is honestly really an honor because we learned about some of these projects in Juan Jose's technology class briefly, and I actually used Rhino Vault for my entire studio project last semester. So, and for those who don't know, that is one of the open source software programs that the BRG has put out. So yeah, it really is truly an honor to have you here and hear you talk live and even be able to ask you some questions. So for my first question, so for my first question, you actually kind of spoke on it just a second ago, but as I understand it, a lot of modern building codes, especially in the US, specify redundancy of structure to ensure stability without fail. So if one unit fails, then the rest of the system sort of accounts for that. But in contrast, you've made these really beautiful geometries in your research that put structure only where the structure needs to be in order to reduce the material input and therefore the embodied carbon. And I also know from a previous lecture that sometimes you've had a hard time finding contractors maybe to make some of the shell structures that you have. And so in the context of all of that, I was wondering, how do you see your materially efficient structures fitting into an industry that is reliant on and sometimes requires redundancy in order to get things built?
Wow, tough question, but a very good one. And I'm very happy to answer this because actually this is indeed a misconception. So people think because we are materially efficient, that means that we design things that are really on the boundary of stability or kind of flirting with redundancy and all the things that you mentioned. In fact, we achieve this in different ways. So it's a different strategy. Like for example, these compressive structures, we don't get the redundancy out of the material strength, but out of the effective thickness and the ability of taking different loading cases. We discretize the structures very precisely in order to control the force flow, but also to allow certain deformation and movements so that the structure can recover. So all these principles are very similar principles why these historic structures are standing. So it's actually, we are never taking shortcuts, right? So we are never taking shortcuts on safety. It's just other principles that we are reintroducing that we believe are equally valid. But then also another example is that, of course, when we do the high-rise construction, then in the boundary conditions of our floor slabs, we make sure that we can never have progressive collapse. So we find alternative load paths. And obviously, we need to demonstrate that in the real project. So maybe what you're also hinting at is that I should perhaps make my presentation less naive in that sense and maybe show a little bit what goes on in the background, because all of these things obviously need to be resolved, because it's not just the US. Of course, also in Switzerland, you need to be able to show alternative load paths if a column gets knocked out. We also, for the project highlow, I didn't say that, but we had to demonstrate what happens when an entire 1 meter patch falls through, what happens when the shell is no longer there and only the stiffeners remain. And so all of these things have been shown. So by the way, the shell would be a situation where the sprinklers don't work and the entire structure kind of deteriorates, then it would still stand with the stiffeners. So what I'm trying to say a bit more in an intuitive way is that there is also a lot of engineering in the background, right? Another question that I often get is that these systems, are they safe in earthquakes? Well, hopefully, what I want to say, yes. So we have to consider earthquakes. We have to consider all these loading cases, and there as well, history has shown us, like, I don't know if you know the nitkamdela shells, but all of these beautiful super thin shells were standing while many of the modern buildings around it were entirely destroyed in the horrible 1980s earthquakes, right? And so there is something about good geometry that helps in all of these things. So I didn't talk about it, but yes, I'm happy that you allow me, at least in not very technical ways though, but to clarify that these important considerations can never be ignored, that they need to be taken into account. We just achieve them through other mechanisms, actually. Yeah.
Right, can you try again to see it works?
Can you hear me now?
Now it works.
Good. I have no idea what was happening. Thank you for the lecture and for the great answer to Isabella's question. I was wondering, you mentioned you're trained as an engineer as well as an architect, and you work in educating architects. Do you believe it would be helpful for more students to be fully trained in both fields, or is there value in specialization? Or put differently, how would you describe the ideal relationship between architects and engineers?
What a great question, but you're going to open a can of worms, because I am extremely thankful that I could start my education with literally a dual degree. And that was so important to lay both bases, because the longer you do something, the more you specialize, it seems that your brain shuts off different parts. And I noticed this very much also in teaching. The first year students coming in are fresh, are interested in everything. So they love my structures classes, but then in year 3, they don't know anything anymore about structures, and structures is not cool, and only shape and space and Swiss boxes are relevant and so on. Now I'm making it a bit in an exaggerated caricature, but I think there is an important value about laying such a foundation. And I think a profile like mine and my team, and what I really advocate for, is an essential profile to bring the design team really together. And I would go even further. What we are also missing is people that can bridge actually the design team, and I'm talking about jointly the architects and the engineers, and then the people that actually realize things on site, because there a lot of lost in translation and a lot of inefficiencies also happen. And so I think we need to bring these two worlds much more together in order really to disrupt and really to do things differently. Because I hope that you appreciate or can imagine that the things that I show didn't happen in a linear project. So you cannot come with a crazy kind of shape and then go to a 3D printer and say like, here, go ahead, 3D print. It's never going to happen. We had worked for 4 years with this specific 3D printing company through Shaj's PhD to really understand all the constraints, to set up pipelines and so on. And this is now for one technique, right? The same with construction companies. And I think it's essential to bring them together. And so, yes, in fact, I'm becoming more and more vocal about this, that I might want to start a new department at ETH that educates little me's. No, I'm joking. People with my background, with interest, with a lot of education in computation, in writing your own solutions, being flexible and so on, and also with that interest and that connection to how things are made, how things are translated on the building side. So yeah, so actually it's funny that you asked this, because this is a very important topic for me, and I indeed strongly believe in a proper base in both fields in order to then bring it together, and then you can still differentiate, right?
Thank you, Philippe. We are running out of time, but maybe we have time for one question from the audience. We have several questions. Unfortunately, we won't have time to address all of them, but maybe you can pick one and
sure. Yeah, there's a lot of great questions in here. One that I'm interested in came from Joan Zhang, who says, thank you for the wonderful presentation. I am curious of the level of effort of computational effort and the training it associates with it. And I'll personally add to that where you think that training should happen, whether in the office, on the student's own time, or in the classroom.
Yeah. I mean, sorry that I'm not succinct with my answers, but these are all very good, loaded and difficult questions. But so the one about computation, Yeah, the earlier you start and embed this really in your way of thinking, yeah, the better that it gets, right? So I would argue indeed that very early on, and that is what we are now doing at TTH in the new curriculum reform. Again, a curriculum reform. We're teaching programming from the first semester, so that this kind of programmatic and also computational thinking is there from the beginning. The efforts. Yeah, I would say the efforts are worth it, because if you tag on to a community or an open source platform, what you actually then get for free is the hard work, the PhD results, all the algorithms of all the other people that came before you. And that is actually, by the way, why we started to develop this framework, because I thought it was not only ridiculous, but also very frustrating that every incoming PhD student had to try to set up their own environment, and they wasted half a year, sometimes even longer, before they could start to dive in and to really solve things or innovate and kind of do. And this same challenge is also true in industry, right? That you see all of these offices, big offices, are all setting up their own connection between engineering, fabrication, and so on. How silly is that? That so much brain power, so much effort is being spent in reinventing the wheel in all your small bubbles. And so I would say increasingly you see indeed open source being important. So yes, it's an effort. I mean, you have to get into it, but the reward is so much bigger. I mean, you get then all this knowledge, all these tools, all these opportunities. So yeah, to me, that is exciting.
Thank you, Philippe. And we would love to continue this fascinating conversation full of relevant topics for the present and for the future of our discipline. I also apologize for people that are, let's say, bringing questions, and unfortunately the students, they have to go back to their studios and we are running out of time. But we would love, Philippe, to have you here and to bring you to Houston very soon with more time, perhaps in another format, with more flexibility also to interact with the students and with the rest of the faculty. In the meantime, thanks for your wonderful lecture and insightful conversation. And to the audience, thank you for joining us, and see you very soon at RISE. Good afternoon and all the best.
Thanks everyone, or thanks y'all.